Alright, so we saw some issues going on through the problems in the last problem set, the 2D kinematics, and I'm going to go ahead and clear up some of those questions. So some of the issues I'm noticing is we are not remembering the two most fundamental things that help make these problems able to be solved. First of all, x and y are independent, and then finally we place our coordinate systems where we find it most convenient. Right, so those are two things that we do need to keep in the back of our mind the entire time while we are working on problems. The next thing we're going to look at is we're going to actually pull up problem 3.18. Right, so problem 3.18 is available in the 2D kinematics homework on Mastering Physics. Normally I'd pull this up, but I'm having some technical difficulties, so we're going to go ahead and work around that. In my problem, we are looking at the fact that we have a soapbox derby car. They are non-motorized cars with very low friction wheels that race by rolling down a hill. We can assume our track begins with a 55-foot long section, and this section is tilted 11 degrees below the horizontal. Well, we can go ahead and start by using our problem-solving techniques. We went ahead and read the problem. We can identify all of our knowns and unknowns. We can sketch our system and all that other fun stuff. We look at the fact that our problem is listed at 11 degrees below the horizontal. Well, if this is my horizontal here, I'm looking at 11 degrees below. All right? This isn't necessarily as useful for me as I'd like, but it's okay, because we are going to look at the fact that we have geometry at our fingertips. Because of alternate interior angles, the ground, the flat ground, is going to be horizontal as well, and this angle down here is also going to be 11 degrees, so it looks a lot more like the problems we've seen previously going on in class. We know the whole length of our ramp is our 55 feet. However, this is not in SI units, so we're going to go ahead to make our lives easier and convert that into meters. When I convert my 55 feet into meters, I get 16.768 meters. Right? I know I only started with sig figs. I am going to keep as many decimal places as possible while I'm doing my calculations to make sure that I'm not losing any information or causing any rounding errors. Right? Well, that's a sketch of our system. That's what's the basic thing that's going on. We want to know, well, part A. Part A is looking at what is our maximum possible acceleration for the car moving down this track. Well, how do we find that out? Well, we need to know how much of our acceleration is in the direction of motion. So, if I go ahead and sketch my soapbox car, which in my case is a box, and I'm looking at the fact that my gravity always acts straight down. This is good old fundamental gravitational acceleration, right? Well, this acceleration is not necessarily all to the advantage of the car. Not all of it's actually going to be happening along the direction of motion. That is because the car itself is only moving back and forth, actually in the case just down the ramp, along the surface of the ramp. This is where that second piece I mentioned before that we need to keep in mind is so fundamental. We need to make sure that we're setting our coordinate systems up where it is most convenient for us. And in my case, we are going to set our y-axis perpendicular to the surface of our hill, and our x-axis is going to be parallel to the surface of our hill. Right? That means we are only interested in what's going on in the x direction. Right? Because that's the only thing that's happening with our box. We're not moving up and down from the ramp. We're just moving down along it. So we can then break our gravitational acceleration into pieces. This is my piece that is perpendicular to my surface, and this is my piece that is parallel to my surface. Right? And I talked to you guys about where does my angle come in. Right? Oops, we'll do green. All right, well, my angle is going to be in this space right here. This angle is going to be equal to this angle of our ramp. So now we can draw what that looks like in a right triangle. If I redraw my right triangle, all right, my x and my y are perpendicular to each other. This is my AX, AY. And this is my AX. My hypotenuse here is my G, and this angle up here is my theta. This is the angle of my hill. Well, using SOHCAHTOA, we can go ahead and find out what AX is. What is the acceleration along the direction of motion? Because this is opposite the side of my angle, I am going to look at the fact that I have sine. So that means my acceleration in the x direction is equal to my gravitational acceleration times my sine of theta. When you go ahead and plug this into your calculator, it is vitally important that you make sure your calculator is in degree mode. I know for your calculus classes that you do have it in radian mode, but for this case you do need to have it in degrees. When I go ahead and plug this into my calculator, I get the fact that my acceleration in the x direction is 1.869928. For sig figs, I'm going to go ahead and round it to 1.9 meters per second squared. This comes from the fact that I had G. G we already know is equal to 9.8 meters per second squared. Right? Sine of 11 degrees does split out a unitless number, so whatever the unit of the number in front of the sine of theta is going to be our unit. So this is the answer to part A. Part B is a little bit different. Part B is looking a lot more like the projectile motion stuff that we've had experience with previously. We are looking at a car starting from rest. It does undergo the acceleration we just found for the full length of our track. Well, we already found out the length of our track. We know our acceleration. We need our final speed. We're going to go ahead and make sure we identify all of our bits of information that we need. We know it's starting from rest, so that means our VXI is equal to 0 meters per second. We know our acceleration is our AX, which is our 1.9 meters per second squared. All right? And we do know that our delta x, our whole length that we traveled, is going to be our 16.768 meters. We are missing one piece of information that we typically have from these problems, and that is time. But we don't need time, because we have equations that are time independent. That brings us to VF squared is equal to VI squared plus 2A delta x. Right? Well, our initial velocity is 0. So that tells us that this term can go away. And we're not looking for VF squared, we're looking for VF. So if we take the square root of both sides, we do get the fact that VF is equal to the square root of 2A delta x. Oops. Alright, so we plug all our numbers in. Our VF is equal to the square root of 2 times 1.9 meters per second squared times our 16.768 meters. And we do finally get a final velocity of 7.9 meters per second at the end of our ramp.